A billion years of evolution versus 14 days of code. Can we match the human ear? That's what we will show you today. We are the Anomaly Pulse Masters, and we will be presenting a solution of the digital ear challenge. Let me present to you the current situation at the Kozel's brewery. There is control engineers around the machinery. When something goes wrong, they can hear it and act upon it. Due to specific reasons in the Kozel's brewery, these control engineers will be moving away from the machines to a control room. But I'm sure you can imagine a lot of use cases for audio monitoring of devices. We are YeastBeat, the monitoring and alerting and detecting solution for managing a factory with a lot of machines or for detecting faults in audio. What we provide. You take a bunch of monitoring devices which are very cheap. You connect them via Wi-Fi to an algorithm. We use a custom algorithm which we will be talking about later, and that can detect and present the mistakes that happened in a very simple web interface. Let me show you, maybe right now is the best time, what we did. I will be having a live demo. So to present to you how this works, I brought a machine. This is an electric toothbrush. Normally, it sounds like this. I'm not sure if the microphone picks it up. It's a slight vibration. What we did at home is did a setup. First, this machine listened to the toothbrush in the normal regime for some time. So right now, it learned what it's supposed to sound like normally. But let's see what happens when I play the normal sound. Please, quiet now. And if I introduce an abnormality by pushing on the toothbrush. Now, we tested this in a very different environment, but let's see if the algorithm has learned how the toothbrush should sound. Okay, so there is no alarm, but we have detected that the toothbrush has been broken. I can play the audio we recorded of that. And the engineer can classify this as an abnormal or a normal audio sample to improve further classification. If I press that this is normal, you won't be alerted about it again. If I do abnormal, on the other hand, it will be more sensitive for this specific anomaly. Now, I believe that. Why? Sorry. I believe that true innovation is built on empiric data and repeatable solutions. So Vicky will explain how this algorithm works.
Thank you. Let me start with summarizing the challenges that we were facing with the development of this approach. The first and foremost, we didn't really have any data to, and even if we had large data sets, the data set wouldn't be labeled, right? We wouldn't really know what sound is normal and what is abnormal. And I'm going to explain this on a traditional supervised machine learning approach. You need to have data and labels corresponding with this data. And the model does a prediction. In this case, it tells us these sounds are normal, these are abnormal. And then we are able to tell if the model was right or not, because we know what is normal and what is abnormal. And we can use this correction information to train the model to predict the labels correctly. But we don't have the labels. So what happens when we don't have the labels? Well, we get a confused AI, and we don't really want that. So we need to be using unsupervised approach, as the previous team mentioned. So what we are doing is that we are not training the model to predict labels for each sound, but we are training the model to say this sound is different than what normal sounds like. The other challenge that we were facing is, again, as the previous team, continuous learning, because normal and what normal is can change. It can change during the aging of the machine on various other factors, so we needed to take this into account as well. And what were the requirements? Well, first, we need to be able to detect anomaly, right? And second, there's even a possibility to detect what kind of anomaly, what sound is. For example, this anomaly is related to, I don't know, broken pump. How do we do that? This is just a brief overview of our ecosystem. Sorry. I'm going to describe individual steps. We'll start with noise filtering. We take a raw audio from the factory, listen closer to the beginning, Ondra will play it for you.
Yeah, the beginning is the most interesting part. Oh, but I don't have the... No.
And I'm going to talk in the meantime. And what we do is that we remove speech and steps and other noises that are not relevant to the task.
Starting pump.
Yeah, the speech in the beginning is a really good example of this. If I play this, it's the same sound tempo, just filtered. You can hear no speech.
The starting pump.
And this is what we can use for the rest of the algorithm. First algorithm that we have is autoencoder model, and I'm going to explain how this works on an example of images so that we can all visualize it better. First, you need a set of images. They can be just normal images. You don't even have to have abnormal image in this set. You need to transform these images and pre-process them. Basically, you downscale them, you lose some information, and then you train a model to rescale the image back into size and as close as possible to the original. And that's pretty much it. How is this useful? Well, what happens if you feed the model abnormal image, right? The model has never seen a cat before. So what's the reasonable thing to do? Well, the reasonable thing to do is to say, yeah, this is a black dog. I've only ever seen dogs in my life. It's obviously a black dog. And this is how we can say that the signal was probably abnormal or different from all the other sounds that we've seen, because
it's unable to be reconstructed.
It should be a cat. The other algorithm that we have works on the principle of vector databases. We take a large amount of numbers, which is the audio input, and using signal processing, such as smell, frequency, etc. coefficients, we are able to take this large amount of numbers and make a small large amount of numbers. And these numbers can then be used to compare similarity. You insert these numbers into a database, and this is a visualization of the database. You can see that the abnormal sounds here in blue tend to be kind of similar with this representation. You can even use this to detect anomaly types, as I was saying before, because, for example, our pipe issues will be close to each other in this space. This also allows for parameterization of the sensitivity. For example, you might want to detect all mistakes and have more false alerts, or vice versa, or you just want to have the most correct classifications, and you can all adjust for this. We tried this. We downloaded a dataset with normal and abnormal sounds of machinery, pumps and valves. We edit noise, and Ondra will play it for you, what it sounds like.
Yeah, you can hear the pump in the background, like a splashing water sound. Then there is a voice, speech, and also some footsteps.
Yeah, the dataset was actually pretty hard because I wasn't able to say what is normal and what's not.
And sometimes there is a sprinkled in abnormal sound, abnormal pump, and we try to detect that.
And we were able to achieve 95% accuracy with this, and Ondra will tell you more.
So by now, you hopefully believe that this works. We tried to show you all the data, so let me tell you the main advantages of this approach. We achieved, I think, a very high accuracy. In all of our datasets, we achieved about 95, 96% accuracy, and we think those datasets are very representative. The implementation of this is very, very straightforward. I basically implemented it right here. All we did before was play this sound to the machine for quite a long time so it can learn how a toothbrush should sound. Now I can basically deploy it, and it will work just as I've shown you. I have already iterated this. Most of AI approaches need people who create a dataset, who listen to the sound and say, is this abnormal, is this normal? We do not need this at all. It self-learns automatically what a toothbrush should sound like. We are very cheap. One of these devices costs 100 euros. So all that you need to do, buy a few devices, let them listen for a few weeks, and you get almost free anomaly detection, and you can analyze it in an app. So, did we match the human ear in 14 days of code? No, but we are 96% there. Thank you for your attention.
Thank you very much. So give the word again to the experts of Asahi, Plzeňský Prazdroj for questions.
Thank you. Thank you again. Thank you very much for awesome presentation. I liked it a lot. We both, I think. And I have maybe some basic questions. The environment in brewery is full of some like disturbing wires. So my question is it necessary to have this device connected just by Wi-Fi, or can you imagine to connect it by wire?
Yeah, it's just internet.
Okay. Maybe very stupid question, but I needed to ask you because I have a bad experience with this kind of Wi-Fi because there are some disturbation. And I wanted to tell you the toothbrush test was absolutely awesome and super. I like it. It's absolutely awesome. Thank you. I think I don't have any questions. Do you have some?
Yeah, thank you. Great presentation. At first, I wasn't sure if it's YeastBeats or YeastBeats, but I know that it's YeastBeats now. My question would be more on, we saw the technical part, which is very interesting and makes sense, more on the human part. Have you thought of the testing process for the employees? Because it's a human factor that plays a role here. Some people hear things, some people don't hear things. So do you have a way in mind how to make sure that the way how you pick the anomalies and normal sounds will be reliable?
Well, the further classification is not actually required because we detect abnormalities anyway, but this can improve performance. So my idea is the best way, the most robust way to do this is to go check physically if there's actually some anomaly happening. And I think that's, and you can fill it out like in an hour, you don't have to report it straight away, classify it straight away.
Yeah, we like the challenge-specific knowledge about the breweries, so it's difficult to answer without consultation because we are not that close to this.
Okay. Yep. Thank you.
Yeah, I think you can detect it by actually looking if some fault happened or not. I think that's the best way.
Okay. I have another question. Have you thought about implementation to our control system? You visit us, so you could see our control system, and I don't understand it. It's like IT thing, but is it possible to, do you think, is it possible to implement it to any control system, or is it necessary to use it like with your application?
Thank you for the question. As you see, the main part is the algorithm itself, which currently runs on the Raspberry Pi boards. And then to show the demonstrate the results, we use the web application for it. And instead of that web application, it can be integrated to the application or a new application or already existing softwares that are the brewers using. So yes, it is very possible to integrate anywhere you want.
Thank you.
A great side product of being such a large team is that we have to make the communication as standard as possible so that we can divide the work and work independently.
Thank you.
Are there any other questions from the audience? Yes?
Hi, thank you for the presentation. We really like it. I have a question regarding the metrics that you used for evaluation of your model. You said that the accuracy is 96%. And yeah, accuracy is quite tricky metric for anomaly detection since you have imbalanced data set, obviously. Do you have a percentage of how many anomalies did you detect?
I do. So the accuracy was built on a 50-50 dataset of half abnormal, half normal. And I will find it here. Sorry, I see it really bad like this.
Yeah, this is partially what I was talking about with the parameterization. So you can kind of tweak it.
Yeah. Okay, so this is like, the sensitivity is a user configurable setting. And the blue one is what percentage of the abnormalities is captured. And the orange one is the percentage of normal sounds flagged as abnormal. So around the 90%, 95%, you get like 95% of true positives and about 5% of false positives.
Yeah, perfect. Thank you.
And we think this will be improved by the classification.
All right, I think we have to wrap it up with that. So big applause for Anomaly Pulse Masters.
Thank you.